Thanks very much. What I'd like to talk to you today about is spectroscopic methods that we're going to use in this experiment. So you've already had some videos that have talked about the general aims of the experiment and also the methodologies that you use to design the calibration curve. I'll talk about that momentarily. But what I really want to focus on today is I want to focus on the actual nature of the spectroscopic methods and how they're different and how they actually create sort of a richness to the data that is quite useful, but also is really distinctive to those spectroscopic methods, and therefore it's useful for us to understand some aspects of that. So let me just first go through the learning objectives that we have for this particular lecture, if you like, and that is that the idea really is at the end of this, you should be able to do the following things. Some of these you're probably familiar with, but you should be able to do the following things. So you should be able to qualitatively describe vibrational spectroscopy. Now, by qualitatively, I really mean diagrammatically explain spectroscopy. That's what when I say qualitatively, that's really what I mean. The second thing is you should be able to convert measurements using the equations as shown here. So this is energy is equal to h nu, where nu is the frequency and h is the Planck constant, is equal to hc over lambda, where c is the speed of light and lambda is the wavelength, and hc nu tilde, where the only new feature here is nu tilde, which is the wave number. The other thing then is, and maybe this is a bit more, it's kind of newer to you, I think, is to recognize the differences between mid-infrared, Raman, and near-infrared spectroscopy, to actually kind of recognize those spectral differences and to be able to identify, if you like, those different types of spectra. To have a qualitative appreciation of vibrational energy levels. So again, that means to be able to diagrammatically explain those types of the sort of thing that's going on with vibrational energy levels. To be able to manipulate the equation nu tilde is equal to 1 over 2 pi c root k over mu. So k then is the force constant, mu is the reduced mass. And that really controls those vibrational energy levels, so it's quite critical in that regard. To be able to explain why Raman, mid-infrared, and near-infrared spectra appear different. As we'll see, they do really look very different, and there's good reasons for that, and it's important to be able to explain that. And then really related to that is to be able to explain the selection rules for each technique and why certain bands are strong, or let me just correct that, or weak in each of the techniques. Okay, so that's basically the idea behind what we're trying to do in this brief video. So in terms of resources that you might use to augment what I'm going to talk about, I mean, generally, it depends where you are in terms of understanding spectroscopy, but this book, despite the fact that it's quite old, this book by Banwell, Fundamentals of Molecular Spectroscopy, is a really good first stab at trying to get some information. I think it's a nicely written book. It's a well-written book. It's fairly clearly explains things and takes its time to explain things, so it's good in that regard. Physical Chemistry by Atkins, of course, sort of tour de force in physical chemistry. It's a very comprehensive book, and the chapters on spectroscopy are thorough. They're quite challenging to read in some cases, and probably cover material very quickly. I think the same would be said of Engel and Reed. Again, a very, very good book, very, very comprehensive piece, textbook, but probably not that user-friendly if you're trying to get your head around something. It can be quite a challenging book to read, but very, very thorough and very comprehensive. So if you really want to understand the details of what I'm going to be talking about and sort of expand upon that, these are the books to reach for, I think. And if you're really just sort of trying to figure out what is going on at all, maybe Banwell is your first port of call. And indeed, quite a lot of you have done 206. I think nearly everyone's done 206. So the other two books that are really worth looking at are Quantitative Chemical Analysis, which is the Harris book. This is the 9th edition. It's in the library. It's the call number for it. Very nice book. I think chapter 18, 19, the sorts of chapters are useful for. I'm going to talk almost exclusively about vibrational spectroscopy. So those are the chapters for that. And then another really excellent book is Principles of Instrumental Analysis. I think this does a better job of looking over vibrational spectroscopy. There's quite a few chapters in vibrational spectroscopy. And there you're looking at, it's also in the science library. It's by Skoog, Holler, and Crouch. These are both excellent resources to look at. So the experiment that you've been doing, or you're sort of currently in the process of doing, is an experiment that's actually really quite important. We sort of think, we often make fun of sort of formulation as if it's not terribly important. It's not terribly glamorous, maybe is the right way to put it. But actually mixing things together properly in the right amounts is pretty important. I mean, there are not too many concrete buildings would exist without the correct mixture of concrete and water, right? So, mixing things together is an important thing to be able to do. And in this experiment, what we've got you to do is we've got you to mix magnesium sulfate heptahydrate, so that's Epsom salts or epsomite, glucose, and benzoic acid. So these are quite different materials. We have an aromatic material. We have a sigma bonded type material, no double bonds, lots of double bonds here. And then we have a mineral. So there's three different classes of materials, if you like, that we're getting you to mix together. And the reason we picked them, I make no, for a good reason, is that their spectral responses are quite different because they're different types of materials. They're also reasonably inexpensive. So from a sustainability point of view, it's better to use, as we're just trying to illustrate how you understand these sorts of things, it's good to use materials that are readily available and reasonably inexpensive. And they do have these very, very different characteristics. So it allows you to see these different spectral characteristics. And of course, you've already looked at this in your design of experiments. What you've looked at is you have a tri-component system, a three-component system. So what you're looking at is how to make a good calibration space. And of course, this is the sort of way you can represent the three-component system in a calibration sort of fashion. And so here, right in the middle is 33% of everyone. And then down here, we would have, if we come to here, we've got 20% of this one. And then we go up to there, 20% of this one, 60% of this one up here, and then 20% across there. So that's the way to read the graph. And you've already decided how best to make your calibration space, however you're going to make it. I mean, you may well have decided these are good spots. I'm making these up. I'm not saying these are good at all, but that's a way of doing some of the calibration space to try and understand what's going on. And there are different ways of doing it, and use design of experiments to decide how best to do that. And it's really actually critically important to understand when you're mixing materials together how much you've used, how well mixed they are, how much you've put in, and how well mixed they are. This is a really important thing to be able to do. And indeed, much of this experiment will test how well you mix things rather than actually rather than much else. And it turns out mixing powder is not so straightforward. I think there's a very nice video about that given to you by Gervais. So those are the sorts of things that the experiment's about. I'm really not going to focus any more on that. I've mentioned it, and that's the last time I'll mention it. What I'm really going to focus on is the spectroscopy, what you measure to understand that componentry. And in that regard, maybe we just think about spectroscopy in a fairly general sense and get some ideas around it. So what is spectroscopy? Well, it tells you about the types, or what does it do, I should say. It tells you about the types of molecules that are in a particular spot and their concentration. That's really what it can do. That's its big capacity. How does it work? So I think this is a pretty nice sort of lay explanation of how it works. I quite like this as an example. I think it gives a good idea of what's going on. And what it really, the way to think about it is that molecules are a bit like tuning forks, right? So you bang a tuning fork, it gives off a certain frequency, and it also gives off the harmonics of that frequency. And a molecule is a bit like a very complicated tuning fork. So, I mean, here is the chord C, right? You can play it on the piano or on the guitar. Well, this is kind of what the signature looks like from a molecule. And you can see there's an awful lot of notes. We have a note here, and we've got a note here, and we've got a note up here, and we've got one here, and we've got one here, and lots and lots and lots. And they're very, very different intensities. They occur at very different wave numbers, which is a way of measuring energy. So there's a lot of different notes with different loudnesses, for want of a better word. And each molecule gives this sort of different spectrum, this unique sort of spectral profile, so you can identify what the molecule is using that information, and that's quite useful. So what are these really to do with? So let me just bear with me while I just flick over. I just need to flick over to PowerPoint for a moment. I'm really just going to use the PowerPoint to illustrate something here. So what we have here is, this is formaldehyde, the molecule formaldehyde, and this is the simulated spectrum. It actually looks very like the spectrum that you would actually see. And the bands are associated with specific vibrations, and you can see that they're animated here in this particular case. So it's quite nice to see them. They're little GIFs, which is why when I do that, they want to stop. And they can provide information about molecular structure. And it's either infrared or Raman, it doesn't really matter. You have these different types of bands, and the molecules are like doing little exercises, if you like. So I always think this one looks rather like someone sort of vaulting over a horse in a gymnasium. And in this case, they bent their back a lot. You know, their heads, the red bit, the oxygen atom is kind of compressed. As they vault over in here, they kind of kept themselves a bit more steady. And in this case, they're stretching out their legs, or if you want to think of it, they're stretching out their arms or whatever. But the point is that they have these different modes of action. We call those normal modes of vibration. And each of them gives you a band. And that's what we see in the spectrum. So that's really what we're looking at. We're looking at these different types of normal modes. And they occur, as you can see, they occur at different energies. Very different energies, in fact. So we'll try and address why that is a little bit later on in a fairly qualitative way, but nonetheless, we'll try and address it. So in terms of that, the music, if you like, that the molecule plays to you, there are two things that matter. So one is the height of the bands, how intense they are. And I'll get onto that a little bit later on. But the other is the frequency, what energy they occur at. So let's just clarify energy. So if we think about energy levels, we should think about it in the following way. So what we have here is we have an equation that relates energy. So let me just write these, just annotate these down. So we have energy here. We have the Planck constant here. We have frequency here. We have wavelength here. We have the speed of light here. And we have the wave number here. Okay, so that's basically what these are. I just show here in this table, I show the various the energies, if you like, are actually in this column here. The energies of the photons or the transitions are quite small. I mean, ranging from 6 times 10 to the minus 19 to 0.25 times 10 to the minus 19 joules. That really corresponds to about 360 kilojoule per mole down to about 15 kilojoule per mole. So almost able to break bonds down to really not able to do anything of the sort. And what do these relate to? So if you think about up here at 9 times 10 to the 14 hertz, that's about 330 nanometers or 30,000 wave numbers. That corresponds to pretty reasonably hard UV. Yeah. In the visible regime, which is just shown here, you're looking at sort of 6 times 10 to the 14 hertz or 500 nanometers, 20,000 wave numbers, about 240 kilojoule per mole. If we come down again, we've got at 1,000 nanometers or 1 micron, you have 3 times 10 to the 14 hertz, 10,000 wave numbers, 120 kilojoule per mole. And that's the near infrared region. Okay, so we're going to talk about that a little bit later on. And then as we go further down, we lose more and more energy. And we end up down here, 0.375 times 10 to the 14 hertz. 8,000 nanometers, 1,250 wave numbers, so a carbon-carbon single bond typically, and down to 15 kilojoule per mole. But so we go from the visible down through the near infrared, down to the infrared. So those are the different regimes that we're going to look at. So what about the measurements? Well, I'll start with the one I think you're most familiar with. So this is mid-infrared spectroscopy. So here's the Bruker Alpha 2. You should all be pretty familiar with that, I hope. And we, remember we place our sample here. We press down with the divot, squeeze it down, and by squeezing it down, we make good contact between the ATR crystal, which is beneath. It's underneath a little diamond window. The ATR crystal then allows the IR light to come in to burrow into the sample. It's called an evanescent wave. And then, of course, the sample absorbs some of the infrared lights. The light that comes out has some absorbance in it, and we're able to detect that absorbance. And I think all of you have done those types of experiments. So what does it look like? What do you get? Well, let's look at some data here. So I'll just move it to there. So I appreciate my face is kind of in the way. In fact, let me just move my face across. The easiest thing to do. That's much better. Okay. So what we have here then is the magnesium sulfate. So the magnesium sulfate has a distinct band here, and then you notice it's got these broader features at these different wave numbers, but it has quite a distinct little band there. Remember, it's a mineral. It's just magnesium sulfate and some waters. Remember, there are 7 waters. In fact, maybe just to be absolutely crystal clear, we should remember that there are 7 waters there as well. Okay, we'll come back to that, but that's kind of an important point. The glucose, as you can see, has a bunch of bands. They're quite spiky looking features, yeah? You'll notice that it has no bands up here. So this is getting up around sort of 1600 wave numbers. So it just totally runs out of bands there. This little feature here is actually due to that diamond window I talked about earlier. And then out here you have the CH regime. So as you can see, it's quite a nice spectrum. It's quite distinct from the magnesium sulfate. They're quite different, so it's quite good. They could easily discern them between these two materials. And then if we go to the benzoic acid, it's different again. Here we have much stronger features here. And of course, benzoic acid has double bonds, which the other ones don't have. Very, very strong features here. And then, of course, extensive sort of CH regime over here as well, because it has OHs and CHs and all the rest of it in slightly different environments. What about Raman spectroscopy? So, well, Raman spectrometer is probably a lot less familiar with. This is one of the ones in our lab, and we actually will have it in the laboratory for you to use. And what it has a laser here. So this is a laser. This is the output of the laser along this fiber optic. You can't quite see it. The picture doesn't show it all, but that comes around to here. And the light comes out here from the fiber optic and shines onto the sample. There's a sample there that it's shining onto. Then the light is scattered back, and the light that's scattered back is then collected in a different fiber and then carried away to the spectrometer, which is over here, and then it's measured. It's as simple as that. And of course, we put a black box over it because we're trying to measure a very weak signal against nothing. Remember that in an infrared experiment, you're measuring absorbance, which is I naught over I, or the log base 10 of I naught over I. In a Raman experiment, you're just measuring some scattering, as we'll talk about a little bit later on. Well, how do these spectra look? Well, they look quite different, don't they, from what we saw previously. The most striking thing, I think, is how narrow the bands are. They're really, really very narrow bands, very distinctive bands. So in the case of the magnesium sulfate, you get a band, which is due to the sulfate. You don't get a lot else. In the case of the glucose, you get these really quite sharp features. And again, it just all stops before we get to 1600, which of course is where the double bond of benzoic acid is. And again, in the case of benzoic acid, the aromatic feature gives us very intense sharp band. That's due to the benzene ring. And then you also have these sharp bands due to the carbonyl from the benzoic acid. So what about near infrared spectroscopy? So again, let me just move my face out of the way here. Here, what we have is, I mean, this is one of the reasons why near-infrared spectroscopy is popular. This is a near-infrared spectrometer, and that's my hand holding it. Yeah, they're very, very small instruments, very easy instruments to use. they can be powered by USB. And basically what they have is they have a light source, or two light sources, sorry, shining onto the sample. The light that comes scattered back, you measure it, and you're able to measure the wavelength from that. And this just shows there's the instrument right there, and there's it with the sample on top of it that's actually measuring. And to give you an idea just how easy it is to use, this is from a couple of years ago. This is a student working in the write-up room. Probably shouldn't be doing the experiment in the write-up room, but there we go. And she was taking samples. She didn't have to take the samples out of the vials. She just put them on top of the instrument. You can see she's actually put a little a glass slide on there because just to support them in the right position. And she was able to show this is her actual substrate content. So there was an active ingredient in those orangey materials. And that's what she got. Sorry, they were the actual measurements. And these are what she was able to predict from the near-infrared spectrum, which you can actually see there. That's just the near-infrared spectrum. And you get it in a few seconds, as you'll see in the examples that you're going to measure. So this just shows then the, let me just move myself out of the way again. This just shows what the spectra look like. Now, first, these spectra don't look great, right? They're pretty nondescript, I think is how you would, I think, reasonably describe them. I mean, they look okay, but they look a bit nondescript. I mean, basically, it's like a bunch of hills. There's a hill there, a hill there, a hill there, and a hill there. Interestingly, you'll notice that the hills there, and there, these hills not that far from each other. They're kind of not that dissimilar. Yeah, so it's kind of interesting that these don't look so different. And this one looks quite a bit different, but the top two kind of look not that different. So maybe near-infrared's not quite as good at discerning these different materials as the other techniques were. But we'll see, we'll see. And this just compares all of the data. So let's just take a moment to have a look at this because I think it's quite informative. Well, a couple of things to realize, right? The really interesting things. Look how different the spectra are in the three different techniques. This is what gives it power. Basically what you're doing, what we call the experiment that you're doing, we call it a multi-mode experiment. So you're using a near-infrared measurement mode, an infrared measurement mode, and a Raman measurement mode. And they allow you to then see things because you get very different responses in the different techniques from the materials. And so your ability to discern, you can sort of see here, they're not so easy to discern, but over here, they're ridiculously easy to discern. So if you sort of use all this material together, it's called data fusion, you could get very, very powerful and advantageous separation. We're not going to do that because we don't quite have time in the experiment to do that. But it just gives you an idea of how these different techniques can work together in a very powerful way because they give rather different responses. That's what's important. So in the case of the Raman, we see these very narrow bands, very, very distinctive, sort of high resolution. In the case of the mid-infrared, the bands are rather broader. You also get some distortion of the bands due to the fact that you get some particle scattering. And then over here, you get the quite bad particle scattering, actually, which distorts the bands again. But you also get these sort of, it's rather like sort of humps. They're almost like UV spectra. They're quite indistinct in some ways. So let's just think about what interactions we're actually measuring. We're actually measuring here. So it's vibrational energy levels. They're all vibrational energy levels. And we can think of that as a diatomic. We can think of one atom here and another atom here. They're different. They have different masses. They're held together by some sort of force, a bit like a spring. And so we have most of the mass of the atoms in the nucleus, so that most of the mass is either here or over here, not much is anywhere else. So, and what's holding it together is spring-like. So you can actually use basically Hooke's law, to try and understand what's going on. So this is just the example of Hooke's law here. Let me just try and move myself out of the way again. So Hooke's law is a wonderful and rather old law or finding. And it's a very simple finding, but very elegant, actually. And it is the restoring force if you pull a rubber band together, pull it apart and you release it. The force is resisting you is actually linear with regard to how much you've pulled it apart, the displacement. So in this particular diagram here, what we're really looking at is that here we would say this is the Q equilibrium or Q0. On this side, you have negative values of Q. And over here, you have positive values. And Q then is, this is the displacement from equilibrium. So it's the displacement from equilibrium that we're looking at. And that basically gives you the following. It's the force is related to minus K, which is the force constant, and then Q, the displacement. And so what that means is that if I'm here, then the restoring force is not that great. And the further away I go, the greater and greater the restoring force gets, but it's linear. So one way that you can actually then work out the energy, if you know the force, you can integrate the formula that gives you the force to get you to the potential energy. And if you do that, I'm not expecting you to memorize this stuff, but I'm just explaining it, is that the restoring force then is going to give you a half kq squared. So it's going to give you a parabolic function, which is exactly what I've drawn here. This is a parabola, it's a half, that's right, a half kq squared. So it's a parabolic function. And that is because the force, the restoring force, is minus kq. And that sort of, I think, makes sense. Because if you imagine it just energies in general, it kind of makes sense that if you have a double bond, this restoring force should be bigger than if you have a single bond, right? So I mean, if you think about, we just think about that for a moment. If I had a double bond or a single bond, it would surely be harder to pull the double bond apart. So it makes sense that the restoring force should be related to whatever the bonding that's holding the system together. So that's the bit that is very, well, basically 17th century mathematics. So that's Hooke's bit. Now it gets a little bit more complicated because when we introduce quantum mechanics, we find something out that's a little bit unusual. So if we look at the diagram, we just looked at it and we said, well, where could you be in this diagram? So let me just, where could you be in this diagram? Well, I could be here, or I could be here, or I could be here. And in Newtonian type of system, I could be at any of these places, absolutely any of them. I could be absolutely anywhere. Yep, like a ball rolling up and down. If I imagine a ball rolling up and down a surface, you know, it could be anywhere in the surface. In fact, when you get down to molecular sizes and molecular dimensions, that's just not the case. And you end up with quantum mechanics, you end up having to quantize the phenomena. And so what happens is that the energy of vibrational levels is related to a vibrational quantum number and some other parameters. One of the key parameters is nu tilde, and nu tilde is related to two things that are quite important. One is the force constant, and the other is the reduced mass. The force constant, I think, makes a lot of sense because, again, as I said before, a double bond should be harder to pull apart than a single bond. So if you imagine plucking a string, it's like it's a stiffer string. It should resonate at a higher frequency. What's maybe, if we use the guitar string analogy a little bit more, if you have a very thick string, one with a big reduced mass, you should get you get a lower note than if you have a very skinny string. So you know the bottom E string on the top of the guitar and the high E string on the bottom. So between the top string and the bottom string, it's E if it's normally tuned, but it's out by about an octave. So, and that's really to do with the diameter of the string. So, or the mass of the string, if you want to think of it in those terms. So that means that reduced mass should also matter, and that kind of makes sense, and we'll have a look at it a little bit later on. So the consequence of this energy quantization is as follows. What you end up with are a bunch of allowed positions, and the allowed positions are as follows. So a couple of things that are interesting. The first is that there is no zero energy. You have a 0 point energy, that's what it's called. And it means if you've got a bond, the molecule always has some energy, which I think kind of makes sense. You can jump between the levels. We'll see that a little bit later on. And that's, of course, where we get this famous equation from that you've met many times. And it's because you jump generally from 0 to 1. That's called a fundamental transition. We're going to talk about overtones a little bit later on, but what I've drawn here, this is a fundamental transition. So that's from V equals 0 to V equals 1. So that's typically the transitions that you normally see if you do a mid-infrared spectrum. So what are the effects of various things? So let's think about a couple of things that can happen. I'm not going to go through all the math here. I don't think I need to, but I would quite like to just explore some of the ideas here. So if you have a single bond, so K of a single bond, so let's just take a CC bond, is about 500 newtons per meter. And K of a double bond is more like 1,000 newtons per meter. So if we just take a CC double bond and a single bond, it stands to reason that K1 then, this would be your CC double bond, this would be your CC single bond. It stands to reason that the frequency should be different because the bonding's different. And that means the parabola is also different, of course, because K1 is greater than K2. So it's a steeper parabola. So it gives you a higher frequency or a higher wave number in this particular case. And you should be able to do those sorts of calculations. They're fairly straightforward to be able to show why materials vibrate in certain places or why bonds vibrate in certain places. And this just shows this for benzoic acid. So what I'm showing here is, well, first we've got our C double bond O, that's this one here. And then I used the best of colors here. We've got our C single bond O, which is this one here. And you can see this is at about 1182 wave numbers. And this one is a much higher up, 1678 wave numbers. And you can do that calculation if you wish. It's not too hard to do, just to convince yourself that they should be different by about that sort of order. So reduced mass is a little bit trickier to deal with. Not so much trickier in a conceptual way. We already talked about the guitar strings, but a bit more tricky mathematically to show. But I've tried to show it here. So I just want us to think about when would it matter? I mean, if you look at these molecules for a moment, carbon, 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 oxygen. So they're all about the same mass. So oxygen's about 16 atomic mass units, carbon's 12. They're not that much different. That's, what is it? I think it's about 2.3 times 10 to the minus 26 and about 2 times 10 to the minus 26 kilograms. So they're not very different in mass. So if you think about it, for quite a lot of things, like for carbon, for nitrogen, for oxygen, they're all quite similar masses. They're really not that different, 12, 14, 16. Things get very different when you then go to hydrogen, however, because it's one. So the three in the top line are sort of in their teens, and then the one below it is 1 atomic mass unit. We don't use atomic mass units, we use kilograms. It's a wee bit frustrating, but it's just what has to be used to get the calculations to work. So if we just do that for a moment, we just think about how that might work. Let's look at a calculation for carbon to carbon single bond. What's the reduced mass? It will be the same for a double bond as well, of course, because the reduced mass doesn't care about the bond order. Well, you've got this is the atomic mass of carbon in kilograms. It's 1.99 times 10 to the minus 26 kilograms. And you multiply it by itself because there's two of them there. And then it's you add the two together. So you get a value of about 1 times 10 to the minus 26 kilograms. And that's a fairly typical value. It doesn't matter if you have a CN bond, an NO bond, a CO bond. They're roughly about 10 to the minus 26, roughly speaking. Things get very different when you put hydrogen in. It's a couple of things to appreciate. So first, when you put hydrogen in, hydrogen has a mass of only 1.67 times 10 to the minus 27. So we just think about some quick and dirty math here. The denominator in the bottom line is about, roughly speaking, is about 1.99 times 10 to the minus 26. Roughly speaking, quick and dirty, right? Just quick and dirty. Yep. So these 10 to the minus 26s are going to cancel out, and you're going to end up with something that's about 10 to the minus 27. So you made a big, big difference there. You made a big difference in the reduced mass. Now, the reduced mass is in the bottom. It's the denominator, right? Square root of the, it's the denominator. You take the square root of it. But what that means is that it's like the very, very thin string in the guitar. It's going to vibrate at a high frequency. And that's exactly what happens. So if we think about the benzoic acid here, we can think about, our C, we can pick our CO, or we can pick a CC, or why don't we just pick the CO, sorry. We can pick the CO bond, and it's going to vibrate at a certain frequency. It'll be about 1185 wave numbers, I think it was, which we looked at earlier on. But if we look at the OH, or we look at a CH, remember these are all CHs, so we look at a CH, that's going to vibrate, even though the force constant's the same, it's going to vibrate at a much higher frequency, up at about 3,000 or even higher, because of the effect, sorry, I got my face out of the way there, because of the effect of the reduced mass. So that's quite an important point to appreciate, a really important point to appreciate. So I'll just, so we can actually see it as a denominator. So that's an important point to think about. Okay, so we've talked up to now about, I think, pretty things that probably you're reasonably familiar with. What are these near-infrared transitions? Well, we just need to think for a moment. What we've got is we have the fundamental, so that's going from 0 to 1, so that's the red arrow as I've shown it here. So that's something like C double bond O. But of course, all these other levels exist. They're all there. It's just, how likely is the transition going to be to get to them? I mean, the levels exist, so you can jump up to them. It's just, is it going to be a very intense transition or not? Well, here's C double bond O. That's the fundamental. So let's just note that down as such, fundamental. And this is for acetone. And then up here, that's called the first overtone. So just to be clear, it's the green transition. So if we look over here, we can just put it in. Yep, there we go. There's the green transition there. That is this guy here. What do you notice? Well, it's about twice what the fundamental was. That makes sense because you're kind of jumping up from there to there. That's 2 H nu, and jumping to there was 1 H nu. So that makes pretty good sense. The intensity looks a bit horrible. It looks pretty weak. It is pretty weak. And so you might say, well, why would you ever use this? Because these are overtones. I get, you can see that they're overtones. That's okay. And they give this near infrared spectrum, and you can see it's near infrared because here we were at what, 1700? This is at about 3400. Next one's up, so we're going to be 4200 roughly, I think. 4100, 5100, sorry. Yep, and so on and so forth. But actually what you normally see, or you normally see CHs. So CH is 3000 here, then there'd be 6000, then there'd be 9000, then there'd be 12,000. So you can see that these are now in the near infrared region, as indeed are these. These are in the near, oh, that's right, that one's not, that's in the near infrared region. So they're in the near infrared region. So just to be clear, this is for the C double bond O, the one that we've shown earlier, and the other ones over here, these are for CHs or OHs or NHs. I bring that up because that turns out to be important a bit later on. Okay, so there we go. That's what we've got. You might well ask yourself, well, why would you do this? This seems a bit daft because look how terrible this band is. It's really, really weak. There's no way you're going to see anything with it. It's a bit of a waste of time. So the answer to that is yes and no. It's a waste of time if you use the instrument that we've got that measured this. You're absolutely right. But it turns out that you can measure these wave numbers much, much more easily using different types of instruments with different types of detectors. Those same instruments are terrible at measuring these energies, but they're quite good at measuring these energies. So actually what you end up with is a situation where you can actually measure these very weak transitions because your light sources and your detectors are very favorable to do that, which is quite nice. So why do the spectra look different? Well, I mean, and they do look different, really, when you look at them. This is magnesium sulfate. So this is the Epsom salt. So this is the Raman spectrum. Beautiful band right there, due to the sulfate. And in the infrared, there's the band there, due to the sulfate. And then you have these other features here. We'll talk about what they are. And you've got, 1, 2, 3, 4, 5, 6 of them. This is the absorbance spectrum going all the way from about 1,000, a few hundred wave numbers, right the way up to about 12,000 wave numbers or 11,000 wave numbers. And you can see that you've got all these various features, and they do look quite different. Well, let's just think about that from what have we got with the magnesium sulfate? So it isn't just a sulfate. So there's a couple of things to realize. The first thing is that the sulfate is an anion. It gives this band here and this band here. That's the sulfate. That's sulfate. It's great. But what else is there? Well, the other thing that's there is water. You've got the water, it's bound here, so you've got it bound, but then you also have water. What does water do? Well, water does lots of things. Water can do the bending mode, and it can also do the stretching modes. So if we look a little bit further along, we look at this spectrum here. Let me just take it to there. So we've got our bending mode there, and we've got our two stretching modes here. The asymmetric stretch at higher frequency and the symmetric stretch at lower frequency. So that's what you've got in there. And then, of course, you have the overtones of that. So those are the overtones. So it's really a nice example to use when you look at magnesium sulfate, because what you're actually looking at is in the Raman experiment, you're looking just at the sulfate, nothing else. That's all you can see. You can't see any of the water, because Raman spectroscopy is actually terrible at measuring water, which is both a good and a bad thing, but it's absolutely horrible at measuring water, and I'll explain to you why in a couple of slides. But on the other side of the ledger, all this is due to these guys here. And there's another, in Epsom salts, there's another water present as well, but the 6 of the waters are coordinated, as I've shown. Okay, so that's what's going on there. So that's kind of interesting. And of course, you can also, always a good idea, you can compare what you've got to the literature. So I pulled this out. I had to do a little bit of manipulation here, but I pulled this out of a very nice paper by a geologist, Crowley. No relation to our James Crowley, but he published this in 1991 with the US Geological Survey. He did a beautiful study of a whole bunch of different minerals, and this is epsomite. Now you'll notice that I've had to turn it upside down and all the rest of it is because he measured it as a transmission spectrum rather than absorbance, but that's okay. But you can see very, very nice correspondence between what he sees and what we see. Really, really nice. And you can click on the link and you can go and read the paper if you want. It's quite nice to look at. It's nice to see what people have done in the past. And also very pleasing that our results look like the results that he gets as well, or he got as well, sorry. Okay, so that's that. What what about what makes these things tick? Why do they look different? Why do the spectra look different? Well, let's start with one that we should, I hope, know, and that's infrared spectroscopy. So many of you will remember that you can think about these in the following way. You can think of it as a molecule having a dipole moment. So I'm going to take water as the example. And I can stretch water out, and I can compress water. So that's the vibrational mode of water. And if I do that, here I have a particular dipole moment. So it has this value here. When I stretch it out, it has a bigger value. I'll put it there. When I compress it, it has a smaller value. I'll put it there. And what you can then do is you can draw a graph, and you can go the change in the dipole moment with the normal coordinate about the equilibrium position is non-zero, and therefore you get an infrared band. I think many of you have done 201 are very familiar with that. It's not a particularly complicated concept. What it's really saying is that the net change in dipole will give you strong infrared bands. So typically, stretching a polar bond will make a big difference. If you think about it, this is a polar bond. Carbonyl, delta plus, delta minus. We know that, again, going back to Chem 191, you'll remember that nucleophilic attack occurs here. Yep. And it occurs at the back of the carbonyl. Occurs at the carbon because the carbon is delta plus. Now, that also makes that makes the chemistry work, but it also makes the infrared spectrum very, very strong because of that very polar bond. Excellent. So that's how infrared works. So it's very clear how that's behaving. And of course, water is great because water has a big dipole. So water gives good infrared spectra. So, you know, one of the issues we saw earlier was that water gives strong infrared spectra. And we saw that in the magnesium sulfate with 7 waters. Very, very, very clear. And we also saw that the Raman didn't do that. So we need to try and understand that. So let's move on to Raman spectroscopy. So here again, I just want to switch to PowerPoint because I've got a couple of diagrams to show. So just let me do that. So I just flick down to the appropriate diagrams and we'll just scoot through them. So the basic idea here, I don't think we need to do very much other than what I've got here, is that if a molecule vibrates, and this just shows molecular vibration, and it shows the molecule, the carbonyls are actually, they're going in and out of phase. So this one's expanding, this one's contracting, and then backwards and forwards like that. And the one that's going down isn't doing anything. And that has a certain frequency. And of course, if I reorganized it and I did a different, we did a different one, what would happen is that, so we have a different vibration here. And now they're all going in and out together in the red. And of course, that has a higher frequency because it requires more energy to do that. And so the curvature of the potential energy surface is really what's giving you that, those different frequencies in that particular case. So in Raman spectroscopy, what happens is that you bring in a particular laser wavelength. And in the example I've shown here, absolutely nothing happens. In fact, I can flick back and show this in the PDF because nothing very exciting is going to happen in this particular case. What we have is we have a vibrational, we have a band coming in. So the laser wavelength's coming in, the molecule does nothing, and the laser wavelength just bounces off. Nothing happens. So in this diagram, the laser wavelength came in. We started at V equals 0. Nothing happened. So the molecule is still at V equals 0. And the light that was scattered off has the same energy as the light that was scattered in. However, let's just think for a moment. What happens if the molecule starts to vibrate? So here, what then happens is that vibration we saw earlier, this sort of vibration now occurs. So now the molecule started to vibrate. Well, the molecule then went from the V equals 0 level to the V equals 1 level. Well, that costs some amount of energy. That costs this amount of energy. So that means that the light that's coming in, the light from the laser wavelength that came in, it has a particular wavelength or a particular frequency, but the light that came out is devoid of that. It lost a little bit of that energy. It lost this amount of the energy, a vibrational quantum. And that's how we got from V equals 0 to V equals 1. And this shows what that looks like. So what actually it looks like is that the difference in energy is depicted here. That difference in energy corresponds to the difference between the laser wavelength, which is set to have 0 Raman shift, and the vibrational mode, which is over here, which has, in this case, about 250 wave numbers of Raman shift. So that way you can actually see all of the vibrational spectrum by scattering light off the molecule rather than absorbing light as you do in an infrared experiment. So the selection rules are really quite different. So what matters here is actually what's called the polarizability. So the polarizability is really related to the stretchiness It's the stretchiness of the electron cloud. That's a strange concept, but just let's think about it for a moment. It's not so different from the dipole moment change that we saw for infrared. It's just that it's not quite the same. So the stretchiness of the electron cloud. So let's just think about that. I'll try and get my face out of the way here. That's better. So what's going on there? What are we seeing? Well, what if we think about what it means? Is that if I imagine a sigma bonded system, the electrons here's a bond. There's one nuclei. There's the other nuclei. It's a sigma bond, so all the electrons are in the middle here, right? If I stretch that out, well, the bond gets a bit bigger, so the sigma bonds, they kind of, the electrons move a little bit, but they don't move very much. So the d alpha beta q is quite small. But if I have a pi system, I have electrons loosely held up here and loosely held down there, and I squeeze the molecule out, I squeeze this vibration out, then this moves a lot, and so the d alpha beta q is large. So the stretchiness of the electron cloud is absolutely critical to the effectiveness of this particular of Raman scattering. And that actually has a really big effect. And let me show it with two examples. Let's just look at the diagram first. What we have is, this is a picture of a starchy type material, or a carbohydrate polymer. And these are components in actually a tablet. So tablets typically contain an active pharmaceutical ingredient, which is this one here. And they also contain a starch. In this particular case, it's the starch anyway. So you can tell it's starch because you see you've got no high frequency fiber, even no double bonds in these two samples. All of these measurements are taken under exactly the same conditions, same amount of time, same laser power, same everything. And you can see that the intensity here of the red material is much, much higher than the intensity of either of the two carbohydrate components. And the reason for that is very, very simple. Conjugation. Conjugation gives you these big pi clouds, and these big pi clouds are very polarizable. So they give very, very strong Raman signals. So a sort of rule of thumb here is that conjugated systems scatter very, very strongly. And extended conjugation gets even better, right? So this is the thing that's important. So let's just think about a couple of extended conjugation systems. Benzene, it's conjugated. It gives a Raman cross section of what's called 30 times 10 to the minus 30 centimeters squared per steroradian per molecule. It's just a measurement. It's just a measurement. Chloroform, which has no double bonds, gives 3. So it's 10 times less effective in Raman scattering. 10 times. But it gets more interesting. If we imagine benzene, so here's our benzene. One benzene ring, that's 30. Well, let's put 2 benzene rings together. Naphthalene, that's 82. That went up by a factor of 3. Let's put in another benzene ring. Why not? Anthracene, 540. It's a big difference. So the more conjugation you have, the more you can get this Raman scattering. So this Raman scattering really, very, very conjugated systems is going to be really, really intense and much more intense compared to the sigma system. So if you think your sigma bonded system is here, your pi bonded system is here, and it makes such a difference to what you actually see. What about near-infrared spectroscopy? That's a bit of a weird one, eh? So near-infrared spectroscopy, it's a bit tricky. So I showed earlier, I drew this diagram earlier, so I'll just draw it again. I'll draw it in a more general form, sorry. So the diagram I drew was of mu versus Q. I did it for water a few slides ago, and I put a couple of points on there. And of course, for, I'm just drawing it like that. Sorry, let me just correct that. So drawing it like that. And we said that for infrared, d mu by dq was non-zero. At equilibrium was non-zero. So it turns out that for near infrared, for the overtones, so this is the jumping from here to here, jumping from here to here, right? What you actually need is the second derivative of that function. So if you think about it, as you know, a wee bit of math will appreciate this, what you actually need is you need something slightly curved. So that plot that I've got there has to look a bit more like this. So the second derivative, so if you think about it, the second derivative d squared mu by dq squared can be non-zero. And it's going to be small. It's always going to be small. But it turns out that it's only really appreciably non-zero if you have very anharmonic potentials. So anharmonic is what I've shown here in purple. And you can see in this case, this is very, very steep. This side is extremely steep. And this side asymptotes to where you break the bond. And that happens. That is really evident. That anharmonicity is really, really evident for CH, OH, and NH bonds. If you've got a light atom, you've got a hydrogen, you see anharmonicity. And that's why the overtones are almost completely dominated by OH, CH, and NH bonds. You get these broad signals. They're often double and triple the values of the fundamentals. Not quite, because as well, the anharmonicity not only creates this asymmetry here, but you'll notice that these levels are getting closer and closer together. So this level is further apart than this level, further apart than this one, and this one. They actually start to compress. And that's actually what you see here. This, again, the point I made a little bit earlier was that look how, you know, magnesium sulfate and glucose were kind of given these signals in roughly the same place. And that's, again, because of the, really a consequence of the fact that you're seeing OHs and CHs, and they're at about the same frequency. So double and triple those is also at about the same frequency. There's a really nice chapter in this book, which actually talks about near-infrared spectroscopy in food science and technology, which is often where it's used. And it's a very, very nice book, and you can just click on the link. It'll take you straight to that chapter, and you can have a quick reread at it if you're interested. Okay, so that, I think, is us more or less done. Let's just go over what we're talking about and see if we've more or less covered everything. So the learning objectives were, we're going to qualitatively describe vibrational spectroscopy. So hopefully one can do that now. Again, using diagrams is often a good way to do that. Convert measurements using the equation Z is equal to H nu, HC over lambda, HC nu tilde. So again, that's a fairly straightforward thing to do based on the table that I provided. And one should be able to do that. Recognize the differences between mid-infrared Raman and near-infrared spectroscopy. Well, that again is very evidential from the shape and general nature of them. And we can see them here. In fact, there's our magnesium sulfate in the Raman, in the mid-infrared, and in the near-infrared. It's a very nice diagram that shows that quite well. Have a qualitative appreciation of the vibrational energy levels. So it really flows from the what we talked about earlier, the V plus a half times HC nu tilde. Be able to manipulate and understand this equation here. Nu tilde is equal to 1 over 2 pi c root k over mu. be able to explain why Raman, mid-infrared, and near-infrared appear different. So we've already discussed that a wee bit about these are very narrow bands and they're different. They're the ones where the D alpha by D, if we just think about it, this is D alpha BDQ. This is related to part 7 as well. This is D mu BDQ. It's this one here, and this is D squared mu BDQ squared. This one's not so easy, I think, to explain, but that's what's going on, at least in a broad sense anyway. To be able to explain the selection rules for each techniques, why bands are strong, strong or weak in each technique. I should also say, just before I finish, I'm just about to finish, you never have to remember the equations. The equations are always given to you, but you do have to be able to manipulate them. Okay, so I hope that was helpful and really explained, got across this idea of why these techniques are different, and indeed how the fact that they're different and the way they interact, light and matter interacts in different ways in these techniques, is actually quite a helpful way to understand these types of phenomena. So thanks very much for your time, and I hope that you find the experiment useful and interesting.